While NASA's space websites flicker offline and Earth's telescopes are blinded by the sun, a third confirmed interstellar object, 3I Atlas, races past Mars at 30 million kilometers. It's the ultimate cosmic irony. Just as this bizarre, emerald-glowing traveler draws closest, America's own science feeds go dark. Only Mars-orbiting spacecraft, from Europe to China and the UAE, can seize the moment and reveal what Earth cannot see, capturing the sharpest images and data before 3I Atlas vanishes forever. But as the world's best instruments pivot under pressure, what will Mars side eyes uncover about this object that defies every comet rulebook? The clock on this alien encounter is already ticking. On October 3, 2025, the solar system's geometry locks Earth out of the action. As 3I/Atlas sweeps past Mars at just 0.2 astronomical units, about 30 million kilometers, the Sun stands directly between us and the comet. From Earth's perspective, the elongation angle, that slice of sky separating the Sun from 3I/Atlas, shrinks to under 10 degrees. For ground-based telescopes, this is a hard stop. Most observatories refuse to risk their optics or their sensors when a target dips below 15 degrees from the Sun. By early October, the comet's position falls well inside that danger zone, not just for a night or two, but for nearly 6 weeks, stretching from late September through early November. Mars, however, sits offset in its orbit by more than 40 degrees. The Sun, 3I/Atlas, Mars angle on October 3rd is broad, often greater than 50 degrees. That means Mars orbiters and surface assets have a clear, unobstructed view, while every eye on Earth is blinded by solar glare. The numbers tell the story. At the moment of closest approach, Earth's view is blocked, but Mars has a front row seat. Any change, any outburst, any anomaly in 3I/Atlas's behavior during this window will be seen first, or only, by the machines circling or crawling on the red planet. For this brief slice of time, Mars becomes the solar system's only watchtower. Every hour lost now is a permanent gap in the record. The window for Mars-side observation isn't measured in weeks or even days. It's a handful of orbits, a sliver of time before the comet speeds away and the geometry changes again. Mission planners, usually working on careful, months-ahead schedules, have to improvise. Standard protocols are set aside for emergency retargeting. Instruments designed to scan Martian valleys or sample the thin air are suddenly aimed into deep space. Data pipelines, calibrated for slow, routine science, are forced to handle bursts of raw telemetry and quick-look images, hoping to catch any outburst or anomaly before it fades. The pressure is relentless. Each pass overhead, each downlink opportunity, might be the last chance to catch a new feature or a sudden flare. There's no time for bureaucracy or second guesses. Everything depends on the speed and flexibility of the teams behind those distant machines. Mars orbits under the watch of multiple spacecraft, each designed for a different slice of the electromagnetic spectrum and each answering to its own mission team. The European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter have secured high-cadence observation slots for the week of October 3rd. Mars Express employs the high-resolution stereo camera and Omega spectrometer to capture multispectral images and analyze chemical signatures from visible to infrared. The Trace Gas Orbiter's NOMAD and ACS spectrometers dissect the comet's light into thousands of wavelengths, searching for rare gases and molecular bands. Both can pivot away from Mars to track the comet, but every maneuver is balanced against thermal and safety constraints. Quick-look data may appear within days, but full public releases typically follow months later after calibration and validation. The United Arab Emirates HOPE orbiter brings a different perspective. Its XI camera and EMU's ultraviolet spectrometer, usually focused on atmospheric science, can be retasked to monitor bright objects in the Martian sky. HOPE's global orbit and flexible pointing make it well-suited for wide-field imaging and ultraviolet spectra, especially if the science team authorizes a rapid response campaign. In past comet and solar storm events, Hope has delivered processed data within a week when results warranted it. China's Tianwen-1, equipped with high and medium-resolution images and a mineralogical spectrometer, could provide context images and near-infrared spectra if retargeted, though official confirmation of a 3I/Atlas campaign is pending. Data from Tianwen-1 typically enters the public domain through curated releases or scientific papers, sometimes weeks or months after collection. NASA's Mars Reconnaissance Orbiter, with the HiRISE camera and CRISM spectrometer, has a track record of comet and asteroid campaigns. Off-nadir targeting depends on pre-approved plans and spacecraft safety. The current US government shutdown complicates public access to new data, even if MRO collects it. Internal teams continue monitoring for spacecraft health and planetary protection. Beyond Mars, the European Space Agency's JUICE spacecraft will attempt to observe 3I/Atlas during its outbound cruise in early November. The geometry is less favorable, and its instruments, JANUS, MAGIS, and UVS, are built for distant, faint targets. Any data JUICE gathers will face a long downlink queue, with public release not expected until early 2026. Even a few spectra or images could help track the comet's activity as it rounds the Sun. This network forms a layered approach, each mission contributing a unique field of view and spectral range. Some results will arrive within days, others only after months of validation. The staggered releases and cross-agency coordination ensure the story of 3I/Atlas will unfold in stages, each dataset a potential clue. 9 minutes. That's the length of the Perseverance rover's unbroken gaze at the Martian sky on October 2nd. Each frame, snapped by the right Mastcam Z, is stamped with a precise UTC timestamp and embedded metadata, exposure time, filter, camera orientation. The sequence was designed for sky surveys, but this time a streak appears. It cuts across the star trails, neither aligned with known satellites nor matching the slow drift of planets. The first step is calibration. Raw images are run through a pipeline, flat-fielded, dark-subtracted, corrected for bad pixels. Every artifact, every cosmic ray, every ghost reflection must be hunted down and ruled out. Mastcam Z's calibration workflow is familiar to its team. Compare the sky background, check radiance units, and align the frames. Only then does the streak stand out, a faint, fast-moving line, consistent in each exposure. Astrometry takes over. Analysts pull the SPICE kernels, NASA's geometric toolkit, to translate the rover's pointing into sky coordinates. The predicted path of 3I/Atlas, derived from JPL Horizon's ephemerides, is overlaid on the image stack. The streak's angle and speed are measured, nearly 400 arcseconds per second, matching the comet's projected motion as seen from Jezero crater at that hour. The direction is right, the rate is right. But coincidence is not confirmation. False positives must be eliminated. Cosmic rays usually leave sharp single-pixel scars, not long, continuous tracks across multiple frames. Internal reflections and ghosting repeat with camera movement, but this streak holds steady. The image processors apply median filters and sigma clipping to weed out transients. Each candidate is measured for flux, checked for any sign of flaring or fading that would betray a camera glitch or Martian dust. Photometry is next. The streak is faint but persistent. Its brightness, measured along its length, aligns with what a diffuse, fast-moving coma would produce at Mars's distance. The light curve is flat, no spikes, no sudden drops. Analysts compare this to models of comet outbursts and solar reflections, nothing out of place. The final test is the fit. The streak's position is plotted against the predicted ephemeris for 3I/ATLAS. The residuals, differences between expected and observed, fall within a few arcseconds, well inside the margin for error at this distance. The evidence mounts, but official confirmation is still out of reach. The US government shutdown leaves JPL's instrument leads silent, their review on hold. Independent analysts like Simeon Schmaus, Shem Aus, publish their findings, but the chain of verification waits for NASA's endorsement. The stakes are high. If this streak is real, it's the first direct detection of an interstellar object from the surface of another planet. But science demands rigor. Each step, calibration, astrometry, photometry, false positive screening, must withstand scrutiny. Until the Mastcam-Z team at Arizona State and JPL weigh in, the community holds its breath. The streak is there, burned into 9 minutes of Martian sky. Whether it becomes a landmark detection or a cautionary tale depends on what comes next. On September 25th, a single amateur observatory in Namibia delivered what would become the last clear portrait of 3I/Atlas before Earth's window snapped shut. The image, taken under southern skies just hours before the comet slipped into solar conjunction, captured an emerald coma stretching nearly 700,000 kilometers across, nearly twice the distance from Earth to the Moon. The core glowed green, a hue that set it apart from most solar system comets. Sunlight, filtered through a cloud of diatomic carbon and other gases, scattered in a way that produced a vivid, almost unnatural color. But the structure was stranger still. Instead of the long, trailing dust tail familiar from textbook comets, 3I/Atlas displayed a sunward anti-tail, a wedge of material pointing toward the sun, not away. This feature, shaped by large, slow-moving grains and the peculiar geometry of its interstellar path, gave the comet a look more like a drifting fan than a classic streak. Fainter shells and arcs rippled outward from the nucleus, suggesting layers or episodes of ejection rather than a steady, wind-blown stream. Follow-up image stacks from September 27th and October 2nd, though noisier and hampered by glare, confirmed the pattern. The coma's boundaries held their shape even as the object faded, resisting the smearing and elongation expected from a typical dust-driven tail. Each new frame reinforced the sense that this was not a standard comet, but something operating under different rules, a visitor with its own internal logic. These snapshots, collected in the last days before Earth's enforced blindness, now serve as the baseline for everything Mars will see next. The numbers behind 3I/Atlas don't line up with any familiar pattern. Start with velocity. Most long-period comets limp into the solar system at 20 or 30 kilometers per second. This object doesn't slow down. It roars past Mars at nearly 60 kilometers per second, and by the time it sweeps through perihelion at the end of October, models project it will spike to 68 kilometers per second. That's a speed that leaves even the fastest solar system comets in the dust. The trajectory is just as strange. Instead of plunging in from some steep random angle, 3I/Atlas hugs the ecliptic, its inclination barely a few degrees off the plane of the planets. For a true interstellar visitor, that's statistically rare. Most are expected to show up from high orbits, not slip in almost unnoticed along the solar system's own highway. Size is the next puzzle. Early brightness estimates, paired with coma models, point to a nucleus at least 5 kilometers across, possibly more. That puts it among the largest interstellar bodies ever observed, rivaling the scale of 2I/Borisov and dwarfing Oumuamua. But the coma itself is even more confounding. Instead of a classic dust tail stretching away from the sun, there's a sprawling, layered envelope. Polarization studies hint at concentric shells or arcs, each one reflecting light in subtly different ways. No long, filamentous tail, just a massive, structured cloud that defies standard comet physics. Polarimetry and imaging both reinforce the anomaly. The coma's green color, driven by diatomic carbon, stands out, but so does its stability. Despite solar heating and a brush with a coronal mass ejection, its morphology barely budges. The numbers, speed, inclination, size, coma structure, stack up into a profile that doesn't fit the cometary mold. For dynamical modelers, each data point is a fresh challenge, and the usual playbook offers few answers. September 25th brought a different kind of test for 3I/Atlas, a coronal mass ejection hurled straight from the sun. Space weather forecasters tracked the CME as it swept through interplanetary space, predicting a surge of charged particles and magnetic turbulence. For most comets, this kind of solar blast is a recipe for chaos. The sudden arrival of energetic plasma can strip ions from the coma, trigger rapid outgassing, and sculpt new tails in a matter of hours. Scientists at plasma labs and solar observatories watched for a textbook response. A shock front, a burst of ionized gas, maybe even a visible kink in the comet's envelope. But the reality was muted. As the CME enveloped 3I/Atlas, ground-based telescopes and Mars-side instruments tracked the aftermath. Instead of a dramatic flare-up or a reshaped coma, the comet's structure barely shifted. The green halo stayed crisp, the anti-tail held its wedge-like form, and the outer shells showed no sign of sudden expansion or fragmentation. Morphological change was minimal: no obvious ion tail, no abrupt brightening, not even a ripple in the coma's layered arcs. For the plasma physicists, this was a puzzle. The expectation was more ionization, a swollen envelope, or at least a hint of magnetic turbulence written into the comet's light. The absence of a strong reaction leaves open questions about the object's composition and internal structure. Is the coma unusually resilient, or is there something about its chemistry that resists solar weather? Without a clear ion tail or a burst of emission lines, the usual diagnostic tools come up short. Researchers now look to Mars orbiter plasma instruments and high-cadence spectra for clues, hoping that somewhere in the raw telemetry, the fingerprints of that solar storm are hidden, waiting to be found. The orbit of 3I/Atlas leaves no doubt about its origin. Its path cuts through the solar system on a hyperbolic trajectory, unbound and never to return, a mathematical fingerprint of interstellar travel. That fact alone places it in rare company, alongside only two previous visitors, 1I/Oumuamua and 2I/Borisov, but the certainty of its origin is only the starting point. The real challenge is what to call it and how far to trust the labels. Some researchers reach for the familiar, interstellar comet, citing the green coma, the outgassing, the layered envelope. Others hesitate, pointing to the missing dust tail, the anti-tail, the stubbornly stable structure, and the high, almost mechanical velocity. The debate is not just about terminology, it's about evidence and the bar for extraordinary claims. Science advances by skepticism, by asking not just what fits, but what survives the next round of data. The lessons of 1I/Oumuamua are fresh. Models multiplied, speculation raced ahead, but only the hard numbers endured. For 3I/Atlas, every anomaly, every odd color, every shell, every unblinking coma must be tested, not hyped. The question is not whether it could be engineered, but whether any measurement compels that leap. Until then, the only certainty is its interstellar passport. Everything else remains a hypothesis, waiting for the next spectrum, the next image, the next surprise. For anyone watching the 3I/Atlas story unfold, the most important tools are public data streams and community-driven analysis. Start with the mission data portals, ESA's Planetary Science Archive, the Emirates Mars Ultraviolet Data Center, and the UAE Hope Mission's open access site. These are the first places to check for quick-look images, spectra, and event alerts. The ExoMars Trace Gas Orbiter and Mars Express will post their initial results within days or weeks, typically as Level 1 or Level 2 FITS files, sometimes accompanied by browse-quality JPEGs. For the fastest updates, independent analyst forums like the Minor Planet mailing list and the Comet Observation Database track raw uploads and flag potential anomalies as soon as they appear. Verification happens in layers. When a new streak or outburst is reported, cross-reference the observation with ephemeris predictions from JPL Horizons or IMCCE. Look for matching detections in overlapping datasets, Mars orbiters, ground-based amateur networks, even solar observatories. Community analysts often publish side-by-side stacks, photometry plots, and motion fits within hours, especially when official channels are slowed by a shutdown or data embargo. To follow the morphology as 3I/Atlas approaches perihelion, monitor the evolution of the coma's structure in each new release. Watch for sudden changes, shells, arcs, or anti-tail brightening that could signal fresh activity. The most revealing science will come from comparing raw, time-stamped images across missions and wavelengths, not waiting for polished press releases. In this moment, transparency and redundancy matter most. Multiple instruments, independent teams, and open release of raw data are the keys to catching what might otherwise slip past unseen. On October 3, 2025, 3I/Atlas passed just 30 million kilometers from Mars, while Earth-based observatories remained blind due to solar conjunction and a US government shutdown. Mars orbiters from ESA, the UAE, China, and NASA became the sole witnesses, capturing data unavailable from Earth. Early images confirmed a green coma over 700,000 kilometers wide and a rapid speed near 60 kilometers per second, but key questions persist. The true composition of 3I/Atlas, the reason for its layered coma, and the absence of a classic dust tail. Despite a close encounter with a solar CME, expected ionization effects were minimal. As international teams process their findings and prepare for staggered data releases, much remains to be explained. The confirmed interstellar origin of 3I/Atlas is not in doubt, but its nature challenges current comet models. Until new data arrives, the story of this visitor is unfinished, reminding us that even with global assets, some cosmic mysteries endure.